About an hour ago, for the first time in my life, I saw a rocket launch right outside. Did someone see it? Was the Starlink awesome, like mind blowing, really cool experience. And it's relevant because this talk is also about rocket launches. So this is a story I stumbled into like a couple years ago and started reading up on it because I found it very interesting. There was a lot to learn. There was a rocket launch in 1996 where it exploded 30 seconds after launch because of a software bug. And I thought a lot of the lessons they learned from it were still relevant today. So we're going to talk about that. But first, a little bit of background on how I even got to this story or why I found it interesting. So I used to work as a penetration tester where we basically tried to find bugs, usually in web applications. So you use tools like Burp Suite and you're identifying bugs. What that really means is you work at a PDF factory. So you convert bugs into PDFs and deliver those to clients, and you do that over and over again, and it gets very repetitive. You're just doing the same thing all the time. So then this is one of my favorite tweets ever. It made me realize that there's like so much more to security about like how do I even detect bad stuff happening. And so I wanted to learn more about like what how do we prevent bad things from happening. And so a quick background on how do I even make a product more secure? If someone asks me to do it, like where do I even start? There's a really good book by Kelly Shortridge where she it's called Security Chaos Engineering, and she mentions that resilience, security is part of resilience, and it's an emergent property of the system as a whole. So you can't measure it only by analyzing individual components. And so to assess the security or resilience of a system as a whole, we tried things like standards and guidelines. I've always tried to find the orange book, the DoD orange book, a physical copy. I would love to get one someday. But the idea is like we're trying to show intent that we're considering how to make a system more secure. But there's even more to that. Like things we don't talk about often is when you join a company and you want to make software secure, how do you do it? There's um how do you work with your engineers, right? Like is there psychological safety? Are you in an environment where you're encouraging your engineers to like you're not adding friction to them, you're actually enabling them to write code in a secure way. So as a security engineer, there's many tools we use, and we're actually me and Omar are actually giving a workshop later today at 5 p.m. about security engineering, where we're going to talk about some of those things. But you have a tool set of tools and processes you use in your pipelines to identify bugs and prevent them. Something happened February of last year. The White House released this white paper on building secure software, and the main points they mentioned, um, well, they did say that the current ecosystem does not sufficiently incentivize the investments required to secure the foundations of cyberspace, which is pretty solid quote. And I was mostly impressed how like official government communications was using words coined by science fiction authors. Like this is the opening to William Gibson's Neuromancer. But the main points they mentioned was one, they talked about like the importance of hardware, which I'm gonna skip this point a bit because I mean, in the case where like you're launching a spaceship, you have full control over your hardware. I work in security engineering for consumer software, which usually you do not control the hardware at all. So that's like a business decision. Then they mentioned briefly formal methods, and so we'll talk about that a little bit. But this essentially, how do you prove that your software is secure or runs correctly? So it's like a mathematical proof that oh, my software behaves as intended. So some compilers and kernels have been formally verified. Does anyone here like work with formal verification at all? Yeah, it's not very common. So actually, I had to like look into like who actually uses formal methods or formal verification in production, and there weren't that many examples. One of them was at Amazon. So they have S2N is their internal TLS library that they use for all of their like internal systems talk to each other through using TLS through S2N. And so they have this interesting paper on how they actually formally verified it. But to summarize, it basically took a team of many people about a year for them to do the initial work, and it takes a lot of effort. And they had to like simplify it into like small components, and those were what was formally verified. Um, so it's not very practical in that like it's very very time consuming. You need a lot of money and effort to formally verify things. Like Amazon can do it, but a small company likely can't. Um, it's also limited to a small component. Now the third part, and we'll talk about the rocket soon, but this is interesting to me. The third part that the White House paper mentioned was memory safe programming languages, and so many people now talk about Rust versus C++, for example. And so essentially, Joe Biden made C++ illegal last year, but they they did want to encourage use of memory safe programming languages, Rust, for example, and there has been research from Google, for example, on how to increase interoperability between Rust and C++, and that allows them to, for example, in the Android system, they can start rewriting components in Rust while some others run in C++. So Google also released a blog post late last year around using or the desire to adopt memory safe languages. And for the components that are still in memory unsafe languages, they wanted to use hardened memory unsafe languages. So we'll talk a lot about this a little bit at the end. There was also the Tractor initiative, which is like translating all C to Rust, but that's a spicy one. I don't know if that you can just rewrite all C in Rust, at least not anytime soon. So the story about the rocket, this was in 1996. That was when Francis McDormand did a killer performance in the movie Fargo. That was also when Tupac was still alive, only for a few months, but he doesn't know that. We're in Kourou, which is a fishing village in French Guyana. It's near the equator in South America. Um, the rocket we're launching is part of the ESA, the European Space Agency, and so French Guyana is a French colony, so they chose to launch the rocket there. And the reason we like to launch rockets near the equator is that your velocity is actually higher. Like if you're standing on the North Pole, you're just like spinning in place. So like your velocity is actually zero. So it helps to be near the equator. And we're launching this rocket today. It's the Ariane 5. You can see it's much chunkier than the other rockets. And that's because it is actually way more powerful. So the previous rockets all launched or had all been launching for a while successfully. There was no issues. And Ariane 5 was a new development, and 1996 today was going to be the first ever time it was launched. And so it exploded. They fished out the black box from Guyanese swampland, and they found that the main reason it blew up was self-destruction for safety reasons. Fine, but what caused that? So one of my coworkers used to be a pilot in the Navy, and he told me about this thing called the Swiss cheese model. It was the first time I hear about that, but it's interesting because it shows that you need many layers of defenses piled up on each other, and then sometimes you can still have an unfortunate series of events that something can traverse through like the hole in multiple slices of Swiss cheese consecutively. And this is kind of what happened here. Like they're launching a rocket, they kind of know what they're doing. So there was many layers of defenses. So many things had to go wrong for this to explode. And so this is what we're going to talk about. So the system where the fault was is called the inertial reference system. So before the rocket launches, it basically calibrates the trajectory to see if it has to make any adjustments to velocity before it launches. So this inertial reference system, I might call it the IRS, was used on the Ariane 4, the previous model, and it was used perfectly fine. It never had any issues. And this system was going to be used, was moved into the Ariane 5 as it is with no changes. So here is some documentation they had showing how it takes, this IRS takes data from the gyrometers, accelerometers, and feeds them into the onboard computer, or like does calculations and feeds the onboard computer or the flight control system um, any changes it has to make to compensate for changes. And so when they were looking at the logs to see what went wrong there, they saw that there was an integer overflow. Essentially, the horizontal velocity was supposed to be a 64-bit float, but it was being stuffed into a 16-bit signed integer in the IRS, and that caused the buffer overflow. So let's think about that a second. Buffer overflow, or in German Pufferüberlauf, is when you have limited memory and you're trying to stuff it into somewhere that's even smaller and it can't even hold it, so you start overwriting other things. Also in 1996 was the famous paper Smashing the Stack for Fun and Profit, um, released. So overflows were becoming more popular back then. But in this case, it was specifically an integer overflow. And my favorite illustration of an integer overflow is when you reach the max and then you add one, it wraps around back to the beginning. So overflows usually cause undefined behavior, which means that we don't know what happens if an overflow happens. I mean, you could crash, you could, like, who knows? It's not defined how the program will behave when you have overflows. And that's the same when if you use an uninitialized variable, or divide by zero, for example. And we have ways to detect that. Like, for example, GCC, you can pass a flag to fsanitize to catch undefined behavior. Now, the good news is that on this rocket, we were not using C or C++. We're actually using the great programming language called Ada, which I think was way ahead of its time. So Ada was back then popular for critical systems. The DoD actually had a mandate in the 90s for all critical systems to use Ada because it was memory safe. Um, and it had good exception handling as well. So in C or C++, if you have integer overflow in a signed integer, it's undefined behavior. But in Ada, it raises a constraint error. And so we can catch exceptions. We know how to catch exceptions. So far, no problem. We know that there's been an integer overflow, but it's something that we can catch. So the Ariane 5, compared to its predecessor, was way, way faster. And so when they were building the system for the Ariane 4, they assumed that it was only ever going to be as fast as like the rocket supported. But the Ariane 5, way, 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 way faster. So the inertial reference system, this was basically right after we launched, within the first few seconds. It detected this integer overflow because we saw that the speed was just way more than we ever imagined it would be. So it saw, okay, I'm seeing an operand error exception because of that integer overflow. And the way they designed the system is that whenever you have an exception, they basically assume that the hardware is faulty. So they just shut the system down and kick off the backup system. They had another IRS just ready to be kicked off. And so what happens when you take a system the exact same system and you give it the exact same input, it's gonna throw the exact same output. So this also shut down. That's fine. We don't need them technically because these were supposed to calibrate the trajectory before liftoff, and at this point we're like a few seconds into the air. So they're just gonna raise an error to the flight control system and tell it like, oh, okay, I have an operand error, but you should be able to handle that. Now, here's the main thing that went wrong is that the flight control system always assumed that it would be getting integer inputs from the IRS. But instead, it got an ASCII string here or an exception. And so it interpreted, instead of interpreting it as an exception, it assumed that it was going to be integer. And so it converted it to a really, really, really long number. So now the flight control system is supposed to compensate for this astronomical number, outrageous number. And so it thought like, okay, we're going way faster than I thought we should be going. And so to compensate for that, let's just tilt the rocket by 90 degrees. So what happens when you have a rocket launching and you do this? So at this point, like the gravitational forces are ripping the hull apart and it's starting to turn into a ballistic missile going down to someone. So the self-destruct program does really, really well and just blows the rocket for safety. Otherwise, it would have fallen on someone. So that's the main reason it exploded. But why did that happen? Like you're talking about some of the smartest rocket scientists with a lot of money. How could they not have caught that this was going to happen? So there was a few reasons. The first one is, oh, well, integer overflows. We know how to catch those. You can just use static analysis. Static analysis is something we're going to be covering in our workshop today at 5. So and they did they ran static analysis on their code and it caught like it had caught potential integer overflows. It caught 7 of them total. And so they thought, what are our assumptions? What are our design decisions? And they noticed, okay, like one of my targets is one of my requirements, I need the maximum CPU utilization of 80%. We read our docs, we read the assumptions, we know that we're using a memory safe language. And so they decided to fix only 4 out of the 7 integer overflows based on their assumptions, which is valid. But you might ask, like, oh, why don't they just fix all of them? Why, like, it's fixing an integer overflow is just adding one if statement. Like, why not do it on all of them? And so here we just have to remember that our phones are 100 times more powerful than the CPU that they were using on the rocket. So back then you had real resource constraints, especially when you had a requirement of um, target CPU util. So they really had to optimize the code, and that this was one way of doing it. Another thing is that this inaugural launch of the rocket was, in a way, the first test of the rocket. It's hard to test rockets because it's expensive. So they were kind of testing in production, and they had made assumptions that one is you log the exception and then you shut the hardware down because the assumption was any error that I encounter is likely a hardware failure, which was more common back then. They didn't think that their software was going to have anything wrong, especially because the IRS was a system that they had used before successfully. They had never encountered any issues, so they just assumed that it was correct. Um, and so in their design docs, you can see that unless proven necessary, they thought it was not wise to make changes to software which already worked well in the Ariane 4. And the saddest part of this was that this inertial reference system was supposed to calibrate the trajectory before the launch, but here it was running after the launch. Why was it even running? And so on the Ariane 4, they just decided to keep it running for like 40 seconds just in case at the last second you had to restart the system because this needed like an hour to restart. So they were like, "Oh, let's just keep it running for a while." But technically, the Ariane 5 didn't even need that because it could restart instantly. So there was absolutely no reason at all to have this running at all. So it was just like legacy code running for no reason. So after the explosion, they um they had a really good post-mortem meeting, like doc and study on what went wrong and why and how to prevent it. And they basically simulated. So initially they would just do like rough tests to make sure things work properly, but in this case, after explosion, they were like, okay, let's simulate the whole trajectory of the flight, like giving it all of the details, all of the coordinates. And they realized that simulating it actually did catch the bug. So they could have caught it just by like simming, basically. So overall, what actually triggered the failure? So it was wrong design decisions or assumptions when they were designing a system, plus undocumented assumptions, which is, for example, the velocity, maximum velocity supported by the IRS, plus reusing software, especially unnecessary software that was legacy, plus a lack of testing, plus a mishandled exception, all of that caused by an integer overflow that they didn't fix. So all of those together caused the failure. And there in the post-mortem doc that they released after, I thought that was very interesting. So they mentioned that it was basically due to a specification and design error. They said that there wasn't enough testing and analysis. And here they admit that previously the view had been taken that software should be considered correct until it is shown to be at fault. And here, this is probably my favorite slide. And then they admitted that now the board is in favor of the opposite view, that software should be assumed to be faulty until applying the currently accepted best practice methods can demonstrate that it is correct. I thought that was very interesting. Now, how exactly do you demonstrate it is correct? That's still not obvious. Still challenging, but I like the idea. So the Ariane 5 overall, the last launch of the Ariane 5 was late in 2023, so it was launching successfully up until like a year and a half ago, and only the first launch failed, and so it was very successful. It even launched the James Webb Space Telescope. And in July of last year, they actually launched the Ariane 6, which someone once asked me, like, but that's an airplane, but it's actually not the airplane, it's the rocket in the background. That's the Ariane 6 that's launching. And so I think these are like really cool photos. Um, Behind the airplane is the Ariane 6 that's launching. So now we're in the sequel to the Ariane 5, I guess. And it didn't explode. So there's other examples of um, software issues like integer overflow. My favorite example of integer overflow ever is this one. Did you get the reference? So thank you, one person who answered. So in Civilization 2, I think, or one of the earlier ones, it's actually kind of now a feature where if you ever take Gandhi or if play against Gandhi, he ends up nuking everyone. And so the theory was that Gandhi was like the least level of aggressive from all of the leaders. And so when you discover the Manhattan Project, it gives you -1 to your level of aggressiveness. So if it's 0 and you do -1, it's actually underflows to the maximum level of aggressiveness, and he nukes everyone. But actually, Sid Meier and the team they said it was actually a myth. It wasn't the actual reason. There was a bug, but it wasn't an integer underflow. But that's probably just my favorite example of like things going wrong in software. There's also more brutal examples like the Therac 25. Was a radiation therapy machine, and it had an integer overflow, but it had a lot of the issues we talked about. But one additional thing was bad UI and bad UX. And so that I think is a very important thing to remember, that like in software security, a bad user interface and user experience can lead to, in this case, actually fatal flaws. And so in this case, the operator of the machine was supposed to set a certain level of radiation, um, and then the machine would like spin in place to apply the, to adjust whatever. I don't know how radiation therapy works. And the problem was, while it was adjusting and spinning in place, the operators were sometimes like entering other commands, and the UI would show that your changes applied, but they wouldn't because it was still like working on spinning. So the UI was showing something, but what's configured in the actual system was something entirely different. And so that actually caused radiation overdose for many patients. So at this point, we know that software can be wrong for many reasons. Like you could catch some of them through static analysis, but some of them are bad design decisions or assumptions. And so, how do we said that in the postmortem, they said like we need to demonstrate that software is correct. So how do you demonstrate that software is correct? So in 1931, this man had written a very interesting paper, and this is Kurt Gödel and his incompleteness theorems. And so essentially, the idea was that in some systems, some statements cannot be neither proven nor disproven within that system. And so those are undecidable statements. And the example, like one example that I like to demonstrate that is like if Pinocchio says, "My nose will now grow," then if he's telling the truth, then it would be a lie and it would grow. But if it grows, then he wouldn't be lying, and so it shouldn't grow. And so, but that's a paradox. So I think it'll just grow and shrink repeatedly very fast, but that is just a paradox. So there's actually this really interesting book that talks a lot about that. Good Leskerbach. Then then Alan Turing extended that to his halting problem and basically saying that a similar paradox to say that for a program given input to that program, I can't tell if the program would halt or not. And so I think there was a Rice's theorem that also extended on that to say like, okay, given that I can't tell if a program halts, I similarly won't ever be able to tell if a program is secure or not. At the very least, you can consider not halting to be the denial of service. So these are for smart people are saying like mathematically, like we probably won't ever be able to tell if a program behaves correctly for certain. So when I'm working with programs, there's no confidence for sure. I can determine like, yeah, I'm certain that this will always behave correctly. Um, yeah, this is what we just talked about. So this kind of going back to the White House's report, formal methods, it's nice in theory, but in practice, what we just talked about, plus that it takes an incredible amount of effort to just apply it to a very, very small subcomponent, given that analyzing components by itself is not sufficient, that's not going to get us where we need. So what about memory safe program languages? The final point that they talked about in the White House report. So we know that there's been recent papers saying that like about 70% of exploitable vulnerabilities were because of memory unsafe languages. So this basically turned into a debate of like Rust versus C++. Um, People get very passionate about language wars, but yeah, even in the case of the rocket, like we know that it's not just memory safety issues that cause rocket explosions or any vulnerability. Like they were using Ada in this case. Um, so not all bugs are related to memory safety, but when we do use C++ or C, which a lot of critical software does use it, we can still write safe software in it. And an example is like jet fighter planes, or there's a lot of critical systems written in C and C++ that don't actually fail. And so because of my background in turning bugs into PDF, I started thinking more about static analysis. And the idea is like static analysis by itself is not a comprehensive security review because it's once again just one component of the entire system as a whole. And just like a brief overview of some of the things we look at. So part of it is running the tool, but part of it is having a process that actually empowers developers to do something with the findings that you have from static analysis. And the way it works is just looks at the code line by line, right? But one thing that it misses is context. So a good example is because it's just using pattern matching, and basically like, some form of regular expressions, you can get it to tell you like, oh, I should never be using AES ECB for encryption. I should instead be using AES GCM instead. That's easy for the static analysis tool to point out. But what it can tell you is that, well, what if I shouldn't be encrypting at all? What if I should be hashing instead, because here we're using it for passwords? So it's never going to have full context. So basically, you run the tool, you try to do some variant analysis, and you send that to the developers, and one of the main dependencies, it just depends on the language you're using. So for example, Ruby on Rails, I like to give that example because you have the holy trinity, I like to call them, like Brakeman, RSpec, and Rubocop, and like with those, it's like the perfect combination of security tools to empower like security engineers to surface whatever behavior they want. But it's not as easy for all languages. And for example, in C++, it's harder to scan C++ simply because it has like rich grammar, and you basically need to wrap around the compiler to effectively to have like accurate findings for C++. So we have seen improvement. Like for example, one of my favorite static analysis tools is SemGrep, and they recently, or like a year ago, released some improvements on being able to do static analysis on C++ without the compiler. So they use treesitter to generate an AST, and they go through it that way, and that's slightly more accurate. But generally, like I used to work at Activision, for example, and we really had to use those like enterprise compilers like Coverity, because well, you had to also wrap them around the compiler and the custom build pipelines they had, because that would give you the most accurate findings for large code bases like Call of Duty. Now, the final challenge is that you can use those tools and they'll surface findings, but then what do you do if you have like 86,000 findings? You just like send them to your developers and say like, good luck, fix it. They're just going to ignore you forever, and never going to talk to you again. So you're supposed to actually triage those findings, combine them into meaningful buckets by remediation, and work with them on resolutions. And so the last part of the slide is, well, can C++ actually be secure? And I think I put this photo because I remember last time I looked it up, the SpaceX software used, I think, in the rockets as well, was actually C++. I could be wrong, but that's how I remember it. Um, so Bjorn Strausstrup, the creator of C++, he had a very, very interesting talk in CPPCon 2023, where he said some of the challenges is that um, in many companies, people were really just writing C/C++, like old versions of it. But he's like, that's not a thing. Like, what is C/C++? Like, you should be really writing contemporary C++, because C++ evolves, and there's like C++23, for example, and they add new features to it, but no one really updates their code to modern versions of C++. And so you have legacy code bases using really old versions. And another problem was when he was talking about Rust, he said like Rust, it's easy to write secure Rust code because you have people who are very passionate about their side projects, like spending a lot of time and effort to write like correct code and good quality code. And that's what you see in a lot of the Rust projects right now. But what about like when it's like just massive enterprisey code by people who hate their lives, and it's a legacy code base that's existed for 30 years, and no one like the people who started don't even work there anymore, and so that's very different. And so like part of it is just like the challenge of maintaining really large code enterprisey code bases, no matter the language, right? Like if you keep using Rust for the next like 40 years, you're gonna end up having really large code bases that are just sloppy. There's also Herb Sutter. Um he does a lot of memory safety stuff, and he has a really really good blog post sometime around last year where he talks a lot about this stuff, including on how to his proposals on how to improve C++ memory safety. But some of my favorite examples are, so Sean Baxter created Circle, and Philip Pislow created PhilC, and those are basically versions of the C programming language that are memory safe. And for example, they also ported a lot of Rust. One of my favorite features of Rust is the compiler. Cargo is really nice to use. And so they're trying to bring some of those features to C++, some of those modern compiler features, but also making the language itself safe. Um, and so that's for basically, if you want to rewrite your entire code base in Rust, well, if someone gives you a memory safe version of C++, you can just move to that instead. You don't have to like change to Rust, right? There's also new proposals being made. And so, for example, I remember speaking with someone about, so we said that uninitialized variables can cause undefined behavior. And so I thought like, well, why don't we just initialize those? Like you can, in the compiler, you can give it, like you can tell it like, okay, if you ever run into an uninitialized variable, just set it to 0. But he made a really good point. He said like, no, but that could be wrong because you're making the assumption that I want those variables to be 0. You're making an assumption that the programmer might not have made. And so I then saw this proposal was to make a default like to basically consider uninitialized variables as erroneous behavior rather than undefined behavior and get the compiler to flag that. Um, and then you had Google with another blog post around like how some of the changes they're doing to C++ to enhance memory safety. Um, but my final two slides, I remember when Python 2 changed to Python 3, and it didn't. Python 3 did not have backwards compatibility, so it was annoying. Like you had like it broke things, right? But they did it. They still did it, and it's like you could still use Python 2 if you wanted to, but if you want to use the modern version, you had to like update your code to Python 3 instead. And so it is feasible, and I think like, oh, maybe C++ can do the same. Like if people are going out of their way to rewrite their code in Rust, then you can just have a version of C++ that's memory safe and get people to update to that the same way people moved from Python 2 to Python 3. Um, my main takeaway is it fine? Can I write secure code in whatever language? And the idea is, yeah, like it doesn't like the language does not matter really. Like you can, with enough effort, tooling, and validating your design assumptions and testing all of that those together, you can make anything secure. And so writing software is hard. Things can sometimes explode, but even when they do explode, it's fine. The rocket was fine. We're on the Ariane 6 now. It's been great. It's launched many satellites. Nothing bad happened. No one died. So yeah, thank you for coming to my talk.